Good evening, ladies and gentlemen. It's January 18 here in Los Angeles, California. I am now on lesson 12 on my channel, and the topic is integral calculus. I am now on lesson 12 on integral calculus. Yesterday, I gave you examples on the evaluation of the integral of trigonometric functions. So for tonight, I will give you some more complicated examples. Okay, let's proceed so not to waste time, okay? Number 1, the integral secant square of theta, tangent square of theta, differential theta. We try to evaluate the value of that integral. Okay, let's proceed with the solution. This should be equal to the integral. We rearrange. We let this tangent square of theta to be tangent of theta all quantity square times secant square of theta differential theta. We just rearrange it. We place it something like it is under the so-called power formula. So if this is under the power formula, we will let u equal to the tangent of theta. The value of u inside the exponent is tangent of theta. Du will be equal to the differential of tangent is secant square of theta, differential theta. It is exact. Same as this. So our assumption that the solution is under the so-called power formula was correct. Because after the verification, the complete value of du is secant square of theta, differential theta. It is exact. So this is actually similar to the integral of u to the n du. And this should be raised equal to u raised to n plus 1 over n plus 1 plus c. Correct? So if we try to follow this one, the final answer should be tangent of theta raised to 2 plus 1, which is 3, all over 3 plus c. Final answer will be 1/3 tangent cube of theta plus capital letter C. Final answer. It seems it is easy, right? As long as we know the formula and we know trigonometric function. Okay, let's proceed with example number 2. A little bit complicated. Evaluate the integral of sine cube of theta, differential theta, all over 1 minus cosine of theta. The numerator is in terms of sine function and the denominator is in terms of the cosine function. So think of the formula and how to evaluate the integral of this that involves sine and cosine. For the meantime, I think we could not integrate the given function. So let's try to manipulate first or rearrange or do something on the given equation for it to be integrable. The integral of this should be equal to the integral. Sine cube can be written as sine square of theta, sine of theta, differential theta. Second power, first power, that's third power. We just expand, okay? All over 1 minus cosine of theta. Then, using our knowledge of identities, we replace this value sine square of theta. Sine square of theta plus cosine square of theta is equal to 1, right? That's under trigonometry. So if we try to compute for the value of sine square of theta, it should be 1 minus cosine square of theta. that will be a replacement for sine square of theta in terms of cosine. So sine square of theta can be written as simply the quantity 1 minus cosine square of theta, sine of theta, differential theta, all over 1 minus cosine of theta. 1 minus cosine square of theta was a perfect square and can be factored out. It's a factorization algebra. 1 minus cosine square of theta is actually the product of 1 plus cosine of theta times 1 minus cosine of theta, right? 1 times 1 is 1. Middle term is cosine of theta minus cosine of theta. It's 0. And the square term will be cosine of theta times minus cosine of theta, and that is cosine square of theta. So the factor form of 1 minus cosine square is actually 1 plus cosine times quantity 1 minus cosine times sine differential theta all over 1 minus cosine of theta. And luckily, cosine of theta and cosine of theta cancels. We got a similar factor on the numerator and denominator, so we can cancel out. So what will remain will be 1 times, what's next? 1 times sine of theta differential of theta is sine of theta differential of theta. We expand now, okay? And 1, cosine of theta times sine of theta differential theta is actually sine of theta cosine of theta differential theta. We expand already after the cancellation. This will be the integral of sine theta differential theta. This will be the integral of sine theta cosine theta differential theta. And these are now factorable. We know the integral of a sine function. We know the integral of the second one falls under the power formula. The value of u is sine of theta, du is cosine of theta differential theta. It is exact. So actually the second one here falls under the power formula. For the first function, it falls under the integral of a sine function. Right? The integral of a sine function is the cosine function, okay, preceded by negative sign. That was formula number 1 on the previous discussion, the last time around, where I made the syntax error. The integral of a sine u du is just negative sine of u plus c, or negative cosine of theta for this problem. Plus, second one, it falls under the power formula. This should be sine of theta raised to 1 plus 1 over 1 plus 1 plus c. Final answer, this should be negative cosine of theta plus 1/2 sine square of theta plus c. Final answer. You see how the solution was arrived at? We do some manipulations using our knowledge of identities under trigonometry. After the simplification, what comes out will be two terms that are integrable by using the given integration formulas under trigonometric. Okay, let's proceed with problem number 3. Problem number 3. A little bit complicated. The integral of sine of 2 theta, sine of 4 theta, differential theta equal to. This is twice theta, this is 4 times theta. So to integrate this one, for the meantime we cannot do anything, not unless we will convert this 4 times theta to a twice theta. We make this similar to this. Okay? This is 4 times theta, this is twice theta. So to integrate it, the angle should be the same for both sine and the sine on the second one. And to do this, we will recall the formula for a double angle under trigonometry. That is, sine of 4 theta is actually sine of 4 theta is 2 theta plus 2 theta, right? 2 plus 2 is 4 theta. And this is similar to the form sine of A plus B. That's under trigonometry. If we try to recall the equivalent of this, just recall your trigonometry. It will be the sine of the first function plus the cosine of the first angle, cosine of the second angle, plus the cosine of the first angle times the sine of the second angle. But luckily for this example, A and B are actually the same. A is equal to twice theta, B is equal to twice theta. Right? So we will substitute the value of A to be twice theta, B to the twice theta also, to this formula to arrive at an angle twice theta, not 4 times theta. So this will become sine of 2 theta, cosine of 2 theta. We are following this. Plus cosine of 2 theta, sine of 2 theta. This term here is similar to this. So what comes out will be twice the first one, should be 2 sine of 2 theta, cosine of 2 theta. As you notice it, the angle is now twice 2 theta. So actually, this sine of 4 theta could be replaced by this value here as a function of a double angle. So meaning, the integral of sine of 2 theta, sine of 4 theta, differential theta, is sine of 2 theta times the equivalent of sine of 4 theta, which was derived from this. Okay? It is 2 sine of 2 theta, cosine of 2 theta, differential theta. The angles are now similar, right? Twice theta, twice theta. This is twice theta, twice theta, twice theta. So they are now similar. And actually we can now proceed with the integration. So if we try to multiply this one, we got sine of 2 theta, sine of 2 theta, that will be sine of 2 theta square. Okay? Cosine of 2 theta, differential theta, we got a 2 here. We bring it out. 2 is out of the integral sign. What remains inside is sine of 2 theta quantity square, cosine of twice 2 theta, differential theta. And I think this is under the power formula. The value of u under the exponent is twice sine of 2 theta. du will be the cosine of the angle, cosine of 2 theta, times the differential of the angle, which is twice differential theta. du will be 2 cosine of 2 theta differential theta. It is not exact. Why? We got a factor 2 here. But there's no problem. I told you, if the only missing term for it to be solvable is a constant, you could introduce that constant for you to bring out the solution. So to counter this 2 here, we will place, we got a 2 originally, right? Then we bring out 1/2, the reciprocal of 2, 1/2, the integral of sine of 2 theta quantity square twice cosine of 2 theta differential theta. And that now falls under the power formula. And luckily, these 2 here cancel with this. If this is under the power formula, the solution now will be sine of 2 theta raised to 2 plus 1, which is 3, all over 3, plus c. The final answer will be 1/3. We got a 3 on the denominator, okay? Sine cube of 2 theta plus c. That's the final answer. It seems it is interesting, ladies and gentlemen. Okay, let's proceed with problem number 4. A little bit complicated as an example number 3. Just to test your knowledge of trigonometry. That's why the topic for tonight is evaluation of integrals involving trigonometric functions. Last example for tonight. The integral of tangent of x over 3 plus cotangent of x over 3, open bracket, close bracket, quantity square times dx. The angle is x over 3 for both tangent and cotangent. So it's a fraction. It's algebra. Okay? I think the proper solution for this is to expand. Expanding. it will be the square root of the first one, so that is tangent square of x over 3. The middle term is twice tangent times cotangent. 2 tangent of x over 3, cotangent of x over 3. The third term is the square of this cotangent. Cotangent is square of x over 3. Okay? We'll go automatic a little bit. We replace this tangent square of x over 3 by secant square of x over 3 minus 1. We got an identity. One plus tangent square of x over 3 is equal to secant square of x over 3. Right? Secant square minus 1. Right, it's right. So if we try to compute for the value of tangent square of x over 3, it will be secant square of x over 3 minus 1. That's this. That's identity, right? Plus 2, tangent is sine over cosine. Cotangent is cosine over sine. Plus, this cosecant square of x over 3 minus 1, it can come from this also. 1 plus cotangent square of x over 3 is equal to cosecant square of x over 3, x over 3. So if we try to take the equivalent of cotangent square of x over 3, it will be cosecant square of x over 3 minus 1. That's this. We use identities. I go automatic a little bit. And for the second term, this cosine cancel with this sine here cancel with this, so this will be 1, right? So 2 times 1, that's 2, right? Okay? And we got a 2 here. Minus 1, minus 1. So actually, the remaining 1 got no more constant. They cancel out. So what will remain will be the integral of secant square of x over 3 dx plus the integral of cosecant square of x over 3 dx. The constant terms cancel out. This is minus 1, this is plus 2, this is minus 1. It will cancel out. Right? And this is 1 also. So what remains is actually this. This is times dx. Right? It is this. And if we try to recall our integration formulas under trigonometric function, we got a formula for this one, we got a formula for this one, we will just only verify the value of u. For the first one, the value of u is x over 3, du is dx over 3. Second one, same, x over 3, du is x over 3. So we are missing 1/3, 1/3. So we will introduce 3 outside of the integral sign. So this will be 3, the integral of secant square dx over 3. 3 and 3 cancels. Actually, that's the original problem, but we must have to introduce this 3 here. Same as for this second one, 3 cosecant square of x over 3 dx over 3. This now falls under tangent, this now falls under cotangent. So this will be 3 tangent of x over 3, that's the integral, plus 3, the integral of cosecant square is negative cotangent of x over 3 plus c. We factor out the 3. Is it correct? No, this should be 3. Sorry for this one. We factor out 3. So 3 times the quantity tangent of x over 3, cotangent of x over 3 plus c. That's the final answer. Have you got it, ladies and gentlemen? The last 3 and 4 examples are a little bit, but they are all good problems for tonight. As I told you the last time around, I will give you a more complicated problems from the previous one. I think this is more complicated from the previous one. Right? We use identities to solve this, and so with this, and so with the second one. Oh, that's integral calculus using integration of trigonometric functions, ladies and gentlemen. I think that's just more than good enough for tonight. So if you like it, please click like. If you want to share it, please click share. And if you want to subscribe to my channel, and I am now on lesson number 12 for integral calculus, please click subscribe. Thank you. Good night, Los Angeles.